Hello and welcome to this presentation related to the gas law. We will consider 5 laws, namely Boyle's law, Charles' law, the pressure law, the combined gas law and the perfect gas law. The gas laws. When considering the expansion or compression of gases, the changes that occur in volume, absolute temperature and absolute pressure are related by the gas laws. And here are the 5 gas laws we will consider within this presentation. Here's the nomenclature used throughout the presentation related to the gas laws. Absolute pressure, capital P, has the SI unit of Newton per meter squared or the Pascal. Volume, capital V, SI unit meter cubed. And the absolute temperature, symbol capital T, has the SI unit of the Kelvin. So those are the parameters used predominantly throughout the gas laws. For example, Boyle's law, P1V1 equals to P2V2. The suffix 1s and 2s relate to different stages within the process. P1 is initial pressure, V1 is the initial volume, P2 in this case will be the final pressure, V2 the final volume. Charles' law, stated as V1 divided by T1 is equal to V2 divided by T2. T1 being the initial temperature of the gas, T2 being the final temperature of the gas within our process. The pressure law, P1 divided by T1 is equal to P2 divided by T2. And the combined gas law, P1 V1 divided by T1 is equal to P2 V2 divided by T2. There's a slight variation for the perfect gas law here. We have PV is equal to MRT. So notice 2 other parameters being used here. M is mass, SI unit of the kilogram, and the symbol capital R relates to the gas constant. That has the unit of joules per kilogram per K, and is written in 2 different formats here, where the R is a function of the gas chemical composition. However, when using the gas laws, we do need to note the following, and this is very important. When using the perfect gas law, shown here, PV is equal to MRT, the pressure must have the SI unit of the Newton per meter squared or Pascal, and the volume must have the SI unit of the meter cubed. It's absolutely essential when using the perfect gas law. However, for all the other laws, we can use any consistent SI units within the formula. So for example, in Boyle's law, Charles' law, pressure law, or the combined gas law, we can use pressure having the unit of the kilopascal, the megapascal, the bar, the Newton per millimeter squared, etc. As long as we are consistent and all pressures will have the same unit, we do not have to worry about using the Newton per meter squared. Likewise, for all the laws except the perfect gas law, we can use volumes in millimeters cubed or centimeters cubed if we so wish, as long as again we are consistent within our calculation that all volumes would be in millimeters cubed or centimeters cubed. However, all temperatures throughout all of the gas laws must always be stated in the Kelvin scale, capital K. That's the thermodynamic temperature scale. So that's very important. All the temperature values, these T values shown here, must always be in Kelvin. There is no exception for that. It's very important. And here are the approximate start times related to the various gas laws contained within the presentation. Should you want to directly review a specific law, for each of the laws, a worked example and 2 exercises are reviewed, but please note all times are generally rounded to the nearest minute. The presentation does conclude with a list of questions for you to attempt at your own pace. So here's some recap slides. Firstly, we need to be able to transpose the gas laws. There's a previous presentation, and it's just an extract here from that presentation showing how we transpose equations such as in the format here of Vp divided by Vs is equal to Np divided by Ns. And we're aiming in this particular case to transpose for Np. Likewise, on the right hand side we have the same formula, but this time we're transposing for Vs. So for this presentation you're expected to be able to transpose equations of that format. there is a separate presentation on the introduction to transposition formulae if you want to recap on this technique. So recap here of some definitions and terminology. Again, from our previous presentation, you need to understand terms of vacuum and gauge pressure. It's very useful for the work we're going to consider. Gauge pressure is pressure measured above atmospheric pressure. Recap continued here. And absolute pressure, which we must use within the gas laws, is measured from a complete vacuum. So it's very important that we understand the difference between gauge pressures and absolute pressures, because very often engineers actually use gauge pressure within calculations, but within the gas laws we must use absolute pressure. So as I said, absolute pressure measured from a complete vacuum. And also, as mentioned previously, we must use the thermodynamic temperature scale, that's the Kelvin scale. And again, a recap here showing the difference between the Celsius scale and the Kelvin scale. So basically, to convert from Celsius degree C scale to the Kelvin scale, we add 273, and to convert from Kelvin into the Celsius scale, we subtract 273. Again, this is a slide extracted from my previous presentation. And finally, I've included some unity brackets here to help us with conversions. So we want to convert, for example, between newtons per millimeter squared and newtons per meter squared, or the bar to Pascal, Newton per millimeter squared to bar, litres to meters cubed, or meters cubed to litres. These are standard unity brackets are often used for such conversions. For your reference, there is a separate presentation on the use of unity brackets. Let's consider Boyle's law. The volume occupied by a fixed mass of gas is inversely proportional to the pressure, provided the temperature remains constant. So diagrammatically, on the left hand side here, we can see as the pressure is increasing, shown by the larger and larger P's, the volume of the gas is proportionally decreasing. So essentially, volume is inversely proportional to the pressure. That's assuming the temperature of the process remains constant. That's often referred to as an isothermal process. So, given that V, being written as inversely proportional to P, can be mathematically expressed as V is equal to constant K multiplied by 1 upon P. So V is equal to K upon P. Rearranging, multiplying both sides by P, we produce the formula P multiplied by V is equal to K, constant. And if P times V is a constant, then pressure P1 multiplied by volume V1 is equal to K, and pressure P2 multiplied by volume V2 is also equal to K. So in essence, Boyle's law can be stated as P1 V1 is equal to P2 V2. Note that pressures P1 and P2 are absolute pressures. Must always use absolute pressures within the gas laws. Just note for reference, of course, we could extend Boyle's law to also include P3 V3. So we have a further stage within our process. Example 1a relates to Boyle's law. A mass of gas has an absolute pressure of 150 kilonewtons per meter squared when occupying a volume of 0.002 meters cubed. If there is no change in temperature during the process, what volume will the same mass of gas occupy when the final pressure is 250 kilonewtons per meter squared? So firstly, let's extract the information from the question. Initial pressure labelled P1, 150 kilonewtons per meter squared, so that's 150 times 10 to the 3 newtons per meter squared, absolute pressure. And the final pressure P2, 250 times 10 to the 3 newtons per meter squared, again absolute pressure. Given the initial volume, labelled V1 here, as 0.002 meters cubed, we've got to find the final volume labelled V2. So from Boyle's law, P1 V1 is equal to P2 V2. We divide both sides by P2 to make V2 the subject. We now simply insert the values for P1 V1 and P2, and evaluating the final volume V2 is 0.0012 meters cubed. So the final volume is smaller than the initial volume, which makes sense because the final pressure is greater than the initial pressure. That relates to our inversely proportional relationship between pressure and volume, or Boyle's law. Here are now some exercises related to Boyle's law. Exercise 1A, a mass of gas has a final pressure of 0.3 meganewtons per meter squared and a final volume 0.002 meters cubed. We've got to find what was the initial volume of the gas if its original pressure was 0.04 meganewtons per meter squared. We assume the temperature remains constant throughout, so again an isothermal process. Answer shown in a bracket here. So I now encourage you to stop the presentation and attempt exercise 1A, applying Boyle's law to determine the original volume V1. Full solution shown on the following slide. Exercise 1A, here's the full solution. As always, extract the information from the question. Pressure P1, pressure P2. Final volume labelled as V2 here. And we've got to determine the initial volume V1. This time transposing for V1, we have P2 and V2 divided by P1. And putting the values, the initial volume V1 is 0.015 meters cubed. I've included here the classroom solution to exercise 1A. This was worked through with the students in the lecture. Exercise 2A. In an isothermal process, constant temperature process, the mass of gas has a volume reduced from 2,400 millimeters cubed to 1,360 millimeters cubed. If the initial pressure of the gas is 0.6 bar, we've got to calculate the final pressure. Answer given in the bracket in two forms here, both in bar and in meganewtons per meter squared. So this time we need to rearrange the equation to find P2. I'd encourage you to stop the presentation, attempt exercise 2A, but the full work solution is shown on the following slide. So exercise 2A, application of Boyle's law again. Again, extracting the information from the question, initial pressure, P1, absolute pressure of course. We've got to calculate the final pressure, so P2 is unknown here. And we're given the initial volume V1 and the final volume V2. Notice they are stated in millimeters cubed, but they're both in millimeters cubed, so I can use them as stated within the Boyle's law. As I stated at the beginning of the presentation, it's only the perfect gas law, or the ideal gas law, where we need to be very careful of the units we're using. So here I'm going to use the V values in millimeters cubed. So again, from Boyle's law, this time we transpose for P2, that's P1, V1, divided by V2. Again, inserting the values. The pressure calculates to be 1.06 bar. P1 is in terms of bar, so P2 is calculated in terms of bar. And I've just shown P2 in terms of meganewtons per meter squared, so my conversion here is to meganewtons per meter squared. So here's the unity bracket conversion, converting 1.06 bar into pascals. That's 1.06 times 10 to the 5 pascals. In terms of engineering notation, that's 0.106 times 10 to the 6 pascals, or of course that's the same as 0.106 megapascals. The answer stated in exercise 2A. Just note with this sentence, I'm actually referring to extracting data from the question, which is not strictly correct. I'm actually extracting information from the question. The word data relates to raw data that might be extracted, for example, from a tensile test, whereas information relates to meaningful interpreted data that provides for parameters, constraints, assumptions, etc., as stated in the questions. I just noticed a slight discrepancy in my terminology after the videos were recorded and edited, so please note that for your reference. And here's exercise 2A, the classroom solution, worked through with the students during the lecture. Charles' law. Charles' law states that the volume occupied by a fixed mass of gas is directly proportional to the temperature, provided the pressure remains constant. So this time volume V is directly proportional to temperature T. You see from our diagrammatic sketch on the left hand side, as the T value increases, so the volume increases proportionally, as long as the pressure will remain constant. In other words, this is termed an isobaric process. So as V is proportional to T, we can write V is equal to K multiplied by T, and simply rearranging V divided by T is equal to K. So again, using our notation of V1, T1 being the volume and temperature at the initial state of the gas, and V2, T2 being the volume and temperature at the final state of the gas, we're able to write Charles' law as shown here. V1 divided by T1 is equal to V2 divided by T2. We must remember though that T1 and T2 are absolute temperatures. They must be stated in Kelvin, essential when applying the gas laws. Let's now consider an example of Charles' law on the following slide. So example 1b, Charles' law. So a gas having a temperature of 20 degrees C occupies a volume of 0.065 meters cubed. We've got to determine the volume the gas will occupy if its temperature is increased to 68 degrees C. So here's our solution. And as always, we extract the information from the question first of all. Note from our recap slide, to convert Celsius temperatures to the absolute Kelvin scale, we need to add 273 to our Celsius temperature. So for T1, that was 20 degrees C stated in the question. We add 273, so the absolute temperature is 293 K, and we do the same for T2, so 68 degrees C, add 273. So 341 K is the absolute temperature for T2. Volume V1 is stated in the question, and we've got to determine V2. So from Charles' law, V1 divided by T1 equals to V2 divided by T2. We simply rearrange for V2, so multiply both sides by T2, so V2 is equal to V1 divided by T1, and that's all multiplied by T2. Inserting the values, we calculate V2 to be 0.0756 meters cubed. There's some exercises now related to Charles' law. Exercise 1b. So a gas is heated to a final temperature of 95 degrees C with an associated volume of 0.23 meters cubed. We've got to find what the initial volume was if the initial temperature is 20 degrees C. We're assuming that the pressure remains constant. Note the hint in the question, temperatures used in the formula must be in Kelvin, not degrees C. There's a hint for us there. The answer is shown in the bracket here. I've stated here the Charles' law formula purely for reference. I now encourage you to stop the presentation and attempt exercise 1b, although the full work solution is shown on the following slide. Exercise 1b, solution. Extracting information from the question, we've got our final temperature is 95 degrees C, so that's T2. We've converted that here by adding 273 to the temperature to determine our final temperature in K, final volume, V2 in this case, 0.23 meters cubed, and we're given the initial temperature, 20 degrees C, and again that's converted into K. I've shown the formula for Charles' law on one line here, V1 divided by T1 equals to V2 divided by T2. We transpose the equation for V1, insert in the values, we calculate the initial volume V1 to be 0.183 meters cubed. And here's the classroom solution worked through with the students during the lecture. Shows our transposition of Charles' law here. Here's exercise 2b related to Charles' law. In an isobaric, that's a constant pressure process, gas at a temperature of 200 degrees C has its volume reduced by 1/5. we've got to calculate the final temperature of the gas. Answer stated in bracket. So again, I would encourage you to stop the presentation and attempt exercise 2b. This time we're rearranging to make T2 the subject of the equation. That's the final temperature of the gas. So be careful with your transposition. But the full work solution is shown on the following slide. Exercise 2b, solution. Extracting the information from the question. In this isobaric process, our gas initial temperature is 200 degrees C. So T1, 200 degrees C, converting to Kelvin, add our 273. We have 473 K, that's an absolute temperature. The question states the volume is reduced by 1/5. So assuming the original volume V1 is 1 meter cubed, then final volume V2 is 4/5 of that 1 meter cubed, so it's 4/5 of a meter cubed, or in decimal that's 0.8 meters cubed. I could of course assume volume 1 is 10 meters cubed, which of course means V2 would then be 8 meters cubed. So as long as I keep the ratio of 4/5 between the values, it doesn't matter what I assume for V1. As an alternative, I could write the relationship between final volume and initial volume as V2 is equal to 0.8 V1, and I could rearrange by dividing throughout by V1, that the ratio V2 divided by V1 is 0.8. So I could use this algebraic approach and literally substitute into Charles' law the ratio of V2 divided by V1, but from my experience, technician engineering students prefer the numerical approach of assuming a numerical value for V1 and proportioning this value to find V2. Now applying Charles' law, we have V1 divided by T1 is equal to V2 divided by T2. Rearranging the equation for T2, we essentially multiply throughout by T2, divide by V1, multiply by T1, and inserting the values we can find T2. That evaluates to 378.4 K, and subtracting 273, that's equivalent to 105.4 degrees C. And here's how we could have directly inserted the ratio V2 divided by V1. Here's exercise 2b, classroom solution, worked through with the students, shows a slightly more detailed transposition of Charles' law. Exercise 2b, we worked here with an alternative solution, and that's just noted in the question that the final volume labelled V2 is 1/5 less than the initial volume labelled V1. So mathematically V2 is 4/5 of V1. Dividing both sides by V1, then V2 divided by V1 is equal to 4/5. Again, as before, rearranging Charles' law for T2, I end up with V2 divided by V1, and we know from above that's 4/5. So again, I can evaluate for T2, and of course we get the same answer as before. Just a slight variation on the solution there in the way it's presented, that's all. Consider the pressure law. If a mass is heated at constant volume, its temperature and pressure will increase. Shown in the diagram here, increasing pressure, we have a proportional increase in temperature. Similarly, if a gas is cooled, the temperature and pressure will both reduce. So P is proportional to T, providing the volume remains constant. So at any stage during either process, that's heating up or cooling down, the ratio of absolute pressure to absolute temperature, T, of the gas will remain constant, C here. Thus we can write the pressure law as P1 divided by T1 equals to P2 divided by T2, where of course P1 and P2 must be absolute pressures and T1 and T2 must be absolute temperatures. Let's now consider an example of the pressure law. Exercise 1C, the solution. Extracting information from the question, T1 120 degrees C, converted to absolute. Temperature here in K, pressure P1, given in the question is 2 megapascals, These are absolute pressures here. Final pressure given in the question, 1.5 megapascals. We have to determine T2 in this particular case. So from the pressure law, we need to rearrange for T2, so you multiply both sides by T2, divide both sides by P1, and multiply both sides by D1. Inserting the values, we find the temperature T2 in terms of K, and of course to determine T2 in terms of Celsius, we now subtract 273 from the K value to get our temperature in degrees C. So that's the solution for exercise 1C. Here's exercise 1C. This is the classroom solution worked through during the lecture with the students. Shows the transposition of the pressure law for T2. Exercise 2C. A gas at a constant pressure is heated at constant volume until the pressure is doubled. If the final temperature is 560 K, we've got to determine the initial temperature in degrees Celsius. We assume no loss of gas during this process. Here's the answer for initial temperature in the bracket. And again, I would encourage you to stop the presentation and attempt exercise 2C. Again, this is application of the pressure law to try and find T1. The full work solution is shown on the following slide. So exercise 2C, here's the solution. Now in this particular question, the final temperature, T2, is given in terms of K, so 560 K is the absolute temperature. We've got to determine the initial temperature, so that's T1 that's unknown here. And we need to state the final answer in degrees Celsius. Now we're given in the question that the pressure is doubled, so we could say that P1 is equal to 1 bar absolute, so that would mean P2 is then 2 bar absolute. So we could use numerical values. We could use P1 is 10 bar and P2 is 20 bar, or P1 is 100 bar, P2 is 200 bar. As long as we keep the ratios being doubled, it doesn't really matter what values we use here. Alternatively, P2 is equal to 2P1, mathematical expression, so we can rearrange that P2 divided by P1 is equal to 2. So different ways of forming the solution here. I find most technician students prefer to have numerical values for P1 and P2 rather than the relationship of P2 divided by P1, but I'll leave that to you to decide what you want to do. So from the pressure law, now we have to find T1. Initially we multiply both sides by T1 and divide both sides by P2, and then multiply both sides by D2. Inserting the values for P1, for P2, and for T2, we can determine the value of T1 in terms of K, and subtract 273, we find the value in terms of degrees C. I would encourage you to stop the presentation and just review that solution so you clearly understand the way we've extracted the information from the question. In fact, the pressure is doubled. We're not given any specific pressure, but the pressures we're using here conform with the requirements of the question. And exercise 2C, classroom solution, showing the transposition of the pressure law for T1. Let's now consider the combined gas law. So if in a process, the pressure, volume, and absolute temperature of the gas changes from P1, V1, T1 to P2, V2, and T2, then provided no change in mass of the gas occurs, then Boyle's law, Charles' law, and the pressure law can be combined as shown here. So now we have P1 V1 divided by T1 is equal to P2 V2 divided by T2. And as always, the pressures are absolute and the temperatures are absolute in Kelvin. Let's consider an example of the use of the combined gas law. Example 1D. A quantity of gas occupies a volume of 0.3 meters cubed at a pressure of 2 bar and a temperature of 12 degrees C. The gas is compressed until its pressure and temperature are 7 bar and 135 degrees C respectively. Assuming no loss of gas, what volume will the gas now occupy? Here's our solution. So extract the information from the question. P1 we can see is 2 bar, P2 is 7 bar, those will be absolute pressures. T1 is 12 degrees C, converting that to K here, and T2 is 135 degrees C, again converted to K, or absolute temperatures. Volume V1 is given as 0.3 meters cubed. We've got to find V2. So from the combined gas law, P1 V1 upon T1 equals to P2 V2 upon T2. We now need to rearrange to find V2. So rearranging for V2, we will need to multiply throughout by T2 and divide throughout by P2. Inserting our values, notice I'm keeping my pressures in terms of bar here, because the units effectively cancel out, so even if I converted them into pascals, I would still get the same answer for V2, and V2 is 0.123 meters cubed. Let's consider some exercises for the combined gas law. Exercise 1D here. We're given the following information about the gas. We've got to calculate the initial value of pressure. So in our first row here of initial values, we're not given the initial pressure, it's unknown. We are given the final pressure. We're given both the initial and final volume and the initial and final temperature in degrees C. Answer for the initial pressure is shown in the bracket in two forms here. So I'd encourage you to stop the presentation, attempt exercise 1D. We're trying to determine P1 in this case, but I'll show you the full work solution on the following slide. Exercise 1D, here's the solution. So from the information given, the only thing we do not know is P1. We have all the other values. Again, as always, make sure we convert our temperatures in degrees C into K. Notice the pressure P2 given is in megapascals, that's absolute pressure of course. T2 also converted into K, and the volumes are given in meters cubed. So from our combined gas law, we now have to rearrange the equation to find P1, so in the unknown we don't have. So to do that, we'll simply multiply both sides by T1 and divide both sides by V1. Inserting the values, notice I put my pressure into the formula in terms of megapascals, so when I evaluate, the answer will be in megapascals, the absolute pressure here. And of course 0.0611 megapascals is the same as 61.1 kilonewtons per meter squared, or the same as 0.611 bar. Back to our conversions again with our unity brackets. For reference, here's the unity bracket conversion, converting from pascals to the bar, so 0.0611 megapascals in this case, and here in terms of pascals, converts to 0.611 bar. Again, notice the cancelling unity bracket feature here, as the pascals in the numerator has to cancel with the pascals in the denominator to leave us with the unit of the bar. Again, that's just for reference. Here's exercise 1D, classroom solution, work through with the students, purely for your reference. Exercise 2D, air is expanded in a cylinder from pressure, temperature and volume of 7 bar, 200 degrees C, and 50 times 10 to the 3 millimeters cubed to a pressure and volume of 2 bar and 200 times 10 to the 3 millimeters cubed respectively. If there is no loss of air during the process, we've got to determine the final temperature of the air. Answer shown in the bracket here. So from the combined gas law, we need to find the value of T2 in this particular case, the final temperature of the air. I encourage you to stop the presentation, attempt exercise 2D, with the full solution shown on the following slide. For exercise 2D, solution, extracting the information from the question, P1 is in terms of bar, as is P2, absolute pressures. V1 is in terms of millimeters cubed, so is V2, millimeters cubed, and temperature T1 is 200 degrees C, converted to the absolute temperature. So in this case, using the combined gas law, we need to find the value of temperature T2. So to rearrange the formula here, we will multiply both sides by T2 and we'll divide both sides by P1, V1 and multiply both sides by T1. Insert in the values. Notice I've kept the pressure in terms of bar and I've kept the volume in terms of millimeters cubed here because the units effectively cancel out. I've got pressure in the numerator and denominator of the equation as I have volume in numerator and denominator, so the units cancel out to leave me with an answer of T2 is 540.6 K, or subtracting 273, that's 267.6 degrees C. Here's exercise 2D, the classroom solution, worked through with the students. Shows a more detailed transposition of the combined gas law. Rearranging here for T2. So finally let's consider the perfect, sometimes called the ideal, gas law. So at temperatures considerably greater than the critical temperature of a fluid, and also at very low pressures, the vapour of a fluid tends to obey the following equation. P multiplied by V, pressure multiplied by volume, is equal to the mass multiplied by R multiplied by temperature T. Just label the equation 1 for reference here. Now, unlike the previous 4 gas laws we've considered, we're able to be a bit more flexible with the units used. With the perfect gas law, we have to be very careful that we use the correct units. So now all pressures P must be in newtons per metre squared or pascals. All volumes must be in meters cubed. And as for all gas laws, the temperature T must be in terms of Kelvin. But now we also need to consider mass M, which must be in kilograms, and what's termed the gas constant R, which is in joules per kilogram per K, shown here in 2 different formats. So as it states here, in practice, no gases rigidly obey this ideal or perfect gas law, but many tend towards it, so that's why it's a useful addition to the gas laws. I have just shown slight rearrangements here of equation 1. Some textbooks do show these versions where dividing throughout by volume V, we have pressure is equal to mass divided by volume, that's all multiplied by R multiplied by T. And if we note that density is actually the mass divided by the volume, then we can also state the equation in terms of P is equal to density symbol rho multiplied by R multiplied by T. But mostly we'll use the format shown in equation 1. For your reference, here are some typical characteristics of gas constants, symbol R, and I've also included a parameter labelled as gamma in some textbooks. Not a parameter we'll be using in this presentation, but it is one that often occurs within this subject area, so just include it for reference here. What we're interested particularly are the gas constants R, and they're usually given in the question, unless the context is an experiment when we're trying to find constant R. There's some typical values of constant R shown here for various gases. Again, just to reiterate what I stated at the beginning of the presentation when using the gas laws, when considering pressure, all pressures must be absolute, and pressure must be stated in terms of Newton per metre squared when using the perfect gas law, but any consistent pressure units can be used in all the other gas equations and laws. Volume must be stated in meters cubed when using the perfect gas law, but any consistent unit of volume can be used when the other gas laws or equations. Now as for temperature, all temperatures without exception must be absolute when using any gas law, and that means they're stated in Kelvin. Let's consider example 1e for the ideal gas. So we're given that a mass of air at a pressure of 5 bar, temperature 45 degrees C, occupies a volume of 450 times 10 to the 3 millimeters cubed. We're given the gas constant, R, is 0.287 kilojoules per kilogram K, so we need to be careful with the information here. We've got to determine the mass of the gas. So extract the information from the question. Pressure is given as 5 bar, I've actually converted that straight into pascals or newtons per meter squared. It's 500 times 10 to the 3 newtons per meter squared, my absolute pressure. Volume V is 450 times 10 to the 3 millimeters cubed, it says in the question. So I'm using a unity bracket here to convert that into meters cubed. Always remember with unity brackets, their term cancel in unity brackets. So my millimeters cubed here has to cancel with the millimeters cubed on the bottom line to leave me in terms of meters cubed. So my volume converts to be 0.45 times 10 to the negative 3 meters cubed. Temperature given is 45 degrees C, converted to K, my absolute temperature. And just note the R value is given as 0.287 kilojoules per kilogram K. So that's equivalent to 287 joules per kilogram K. So from the ideal or perfect gas law, we know PV is equal to MRT. We have to rearrange for M. In this case, mass M is equal to PV divided by RT. In other words, divide both sides by RT here. Inserting the values for pressure, volume, R, and T, our mass evaluates to 0.0025 kilograms, 2.5 grams in other words. So as I said many times now, be careful of the units you use with the ideal or perfect gas law. You have to be very precise with the units. Exercise 1E. In an experiment to determine the specific gas constant, R or air, the following data were gathered with a volume of 0.4 meters cubed, a temperature of 15 degrees C, a mass of 500 grams. If the experiment was undertaken in atmospheric conditions, so 1 bar pressure assumed, we've got to find the value of R. Answer given in the bracket here. So here's the perfect gas law. I'd encourage you to stop the presentation and attempt this exercise. We're trying to find the gas constant R. Full work solution is shown on the following slide. Here's exercise 1E, solution. I'll let you work through this at your own pace. Just notice that the mass was given in the question as 500 grams. I've obviously converted that into kilograms here for the perfect gas law. An atmospheric pressure, P, assumed to be 1 bar. That's equivalent to 10 to the 5 pascals for absolute pressure. And as always, T is converted into K for our absolute temperature. Rearranging the equation for R, we simply divide both sides by M and T, and inserting the values, we determine the value of R, joules per kilogram K. That's the solution for exercise 1E. Here's exercise 1E, the classroom solution. Shows rearrangement here of the perfect or ideal gas law. And exercise 2E, a cylinder of volume 50 times 10 to the 3 centimeters cubed contains 0.25 kilograms of argon at a temperature of 30 degrees C. In this case, we're given the gas characteristic for argon, which is 208 joules per kilogram K. We've got to determine the pressure in the argon. Answer is shown in the bracket here. Once again, I'd encourage you to stop the presentation and attempt this exercise. This time we're calculating the pressure P, shown here. Full work solution is shown on the following slide. Exercise 2E. Notice that the volume was given as 50 times 10 to the 3 centimeters cubed. So again, I've used a unity bracket here to convert my centimeters cubed into meters cubed. So I must use mass given in the question, R given in the question, and a temperature converted from 30 degrees C to 303 K, absolute temperature. From the ideal gas law, PV equals MRT, we rearrange this time for P, and inserting the values, we find that P is 315.12 kilonewtons per meter squared, or that could be stated as 3.15 bar to 2 decimal places. Here's exercise 2E, the classroom work solution. Perfect or ideal gas law, rearranging for P. Here's a slide of useful conversions, purely for your reference. It lists typical conversions for pressure, for volume. It shows pressure conversions between bar pascals, millimeters of mercury, and meters of water, fresh water, and a typical atmospheric pressure, again in pascals, millimeters of mercury and water. And a typical unity bracket for converting pressure from pascals in gauge pressure to the bar in absolute pressure is shown here. Finally, I'll leave you with some tutorial questions to undertake at your own pace and assume that all pressures stated are absolute unless told otherwise. Here's question 1 and question 2. Answers are always shown in the brackets on the right hand side of the slide. I'll let you determine, where appropriate, the gas law to use. There's a choice of 5 gas laws, of course, but hopefully when you extract the information from the question, you'll see which gas law is most appropriate. Question 3 through to question 5. Answers in brackets. Boyle questions continued. Question 6, question 7. Answers shown here. Question 8 through to question 10. Answers here. Question 11 through to question 13. Answers here. And here's tutorial questions 14 through to 16. Just note in question 14, 2 gas laws are required within the solution. Firstly, the combined gas law to find the initial temperature, and secondly, the perfect gas law to find the mass of the gas. Question 16, again 2 gas laws are required. First to find the original volume, and the second to find the final temperature of the oxygen. I'll let you read the question at your own pace and decide which laws to use. And finally, question 17 and question 18, with the answers shown here. Read question 17 and 18 very carefully, because they have various stages within their process. So you may have a stage 1 process, to a stage 2 process, and then to a stage 3 process. I'll let you think through the problem yourself. As I said, extract the information very carefully and see which gas laws are appropriate in the various stages of the processes outlined. A bit more thought-provoking questions 17 and 18. And for your reference, I have included the full work solution to question 17 here. I'm going to let you review this at your own pace. This is the solution for part A, calculating pressure P2. Question 17 continued, the solution for part B, calculating temperature T3. And question 17 continued, part C, calculating the temperature T4. Here's the solution for question 18. Again, I'll let you review this at your own pace. Information extracted from the question on this slide. Question 18 continued. Here we calculate temperature T2. Question 18 continued. Here we calculate temperature T3 and also the mass of the gas. Here's the bibliography used to help generate the presentation, which I hope has been of some use to you. And as always, thank you for viewing.